hard to like be content with like physics.
You never go back.
Yeah, you're just used to the rigor. It becomes like.
It becomes a new standard.
Yeah.
Yeah.
Yeah, that's why I never went to physics. Couldn't.
You speak Spanish?
Yeah. You?
Yeah.
Yeah. Nice. Yeah, I think I saw you with.
Oh, Danesh?
No, with Eduardo. I think. Have you spoken Spanish with him?
Maybe once. Yeah.
I feel like I've overheard that.
I usually speak English to him though.
I see. I spoke Spanish with him.
Oh yeah?
Yeah. When he told the story about he went to Israel, I think, and he said about yeah, he talked about Perez, but he also talked about there was it a statue or like this old. There's this like place where they speak like this very old Spanish.
Yeah. It was because they're part of like the Jewish community. That's
yes,
like
yeah,
different kind of Spanish.
Yeah, so he was explaining to me. We were talking Spanish about that. Like,
oh, word.
Yeah, he was showing it to me. It was really funny.
Yeah. Like he was actually speaking it to you.
Yeah. He was telling me like that. I wasn't sure like what, because usually I'm not very like PC sometimes because I grew up in South America, so I'm used to it, and I wasn't sure if when he showed me that thing, I was gonna say the way because he showed me like how they write, and I was gonna say like that they write like poor people. And I'm like, I stopped myself for a second, and he understood what I was trying to say. That was one thing, like, yeah, oh shit, nice. Yeah, they do that. So they're right. Yeah. Anyway. That's jokes.
Where are you from, bro, in South America?
From Ecuador.
Oh, nice.
You?
I was born in Venezuela.
Oh, very nice.
I grew up in Mexico.
Okay, I had the impression you were from Mexico.
Yeah. Schizophrenic rambling, huh?
Yeah, it's necessary.
Necessary.
That's some schizophrenic rambling.
Jonathan will be here soon.
Oh yeah? How soon? What did he say?
Well, 4 or 5 he said he'll be here at least 15 minutes later.
Oh well.
So he should be here soon by you.
Cool. Well, I'm recording.
Yeah,
I think I'll start. It won't be that much.
Yeah.
Okay. Oh, it's not gonna pick up this upper board though.
I can change, like, rotate it.
Hold up. We just
But
need to.
the thing is, I can't see where it's pointing. Like,
I can fix it. Hold on.
if you bring your laptop here, I can rotate it for you.
There's too many things going on.
Oh, I see.
So.
Okay.
Just gonna get the good.
Slept like 3 hours last night. Sorry, so.
I slept 3 hours the night before, and yesterday.
Okay, that's good.
I slept 11 hours.
That'll be me tonight.
Yeah.
Good to go?
Yeah, good to go?
Yeah.
All right, welcome everyone. I am going to be talking about spectral geometry, some Riemannian geometry, basically everything to do with the Laplacian. So, to start, I know some of you haven't seen Riemannian geometry in detail, so I'm just going to give like a brief overview of that. Then we'll talk about the Laplacian, what it is on Riemannian manifolds. Then some Hodge theory, which is sort of like the bridge between the spectrum of the Laplace operator on manifolds and the theory of de Rham structures, like the de Rham cohomology. And schizophrenic ramblings at the end. We'll talk about the real core of spectral geometry, which is like what the spectrum of the Laplacian can tell us about Riemannian manifolds. Okay, so just some basic definitions from Riemannian geometry. A Riemannian manifold is a manifold with a symmetric tensor G. That's defined at every point on each tangent space that's symmetric. And it's non-degenerate, so if this is equal to 0 for all yp, given a certain xp, then, or if this is 0 for all yp, that implies that xp has to be 0. So that basically what this tells you is that the matrix given by taking components of this thing is invertible. In regular Riemannian geometry, you also ask for this thing to be positive, and that's the setting that we'll be working with today. So we're going to be working with just a regular Riemannian metric, so this is also positive. Okay? So a Riemannian manifold is just a manifold with one of these metrics. So you can take any manifold and equip it with a Riemannian metric, any smooth manifold, and equip it with a Riemannian metric. So there's a small theorem which says that every smooth manifold M has like lots of Riemannian metrics. And to prove this, you can just use partitions of unity. Of your underlying manifold, and on those on that open cover, you can pick Riemannian metrics on Rn and just pull them back to each of those open sets, and we glue them all together to get one big metric on that smooth manifold. And so that's why we'll have lots, in general, lots of Riemannian metrics on smooth manifolds. Okay, good. So in general, on a general Riemannian manifold, we have like the space of vectors or vector fields and the space of forms, and those are not in general canonically isomorphic. They have the same dimension, but they don't necessarily always have a coordinate independent isomorphism between them. But adding a G will basically give us a nice coordinate invariant canonical isomorphism between the tangent and the cotangent bundle. So we have a map that we call flat that goes from TPM to TP star M, and this map is just given by take the vector xp and map it to GP, map it to the map that takes YP and returns G of XP by P. So basically, you're just mapping it to like the linear map, which just puts YP in the second component. Okay, so this is going to be a map between TP and TP star, because this is obviously a linear form. And it's also an isomorphism because GP, we picked it to be non-degenerate. Okay, so you can show that the kernel, of course, of flat is going to be basically those vectors YP such that GP of XP YP is 0 for all XP. But by definition, because we chose it to be non-degenerate, this is going to be 0. So that means that we can actually invert this map and obtain sharp, which is a map that goes from TP star M into TPM, which is just the inverse of this mapping. Okay. Okay, any questions just about these basic constructions? Okay, good. Okay, this also having this sharp map. So they're called lowering and raising in physics. They usually call them lowering. Yeah.
Sorry, is like would the inverse just be like setting the other one to a number and then like going over all like the y's?
Sorry.
So like you mapping your x and then like you take that x and then you like you take this map from y to so you kind of like set that thing that x is like to your value and then you just go it's a function over all y's, right? Would the invertible just the inverse just be like setting the other one constant?
The inverse you can express it with the metric that I'm going to write down right now, which is like in terms of like the metric that is induced on here. But it's not immediately obvious how to write the inverse of this mapping. We just know it's invertible because it's kernel 0, so as vector space isomorphisms, we know that it's going to be invertible. But yeah, I can show you how you write the inverse now. So having this sharp will give us a metric induced on, we'll call it G inverse P. It's going to be a tensor, a metric on the dual tangent spaces, and it's just going to be defined by, if I take two forms at a point, by this mapping sharp, I'm able to map them down to vectors at a point. And then, of course, I have G, which is the metric on vectors, and then I can just take GP on those two vectors. So you can show very easily that this is also a metric, so it satisfies all the definitions of the metric, and so it's a metric on our cotangent spaces now. Yeah, so if you're asking about the inverse will just be the map like GP inverse of, you take alpha and then you leave that slot open, so then you can get something like that, right? And then, of course, with the identification that the double dual is equal to the original space. Okay. Any? Good. So now we have a metric on the cotangent spaces. But we're generally interested also in forms. And we can actually also induce metrics on all K-forms. So we have metrics, usually called wedge KGP, and we can do it on wedge K TP star M. Wedge K TP star M into R. And how is this defined? If I have, well, I'll define it on decomposable forms, and then I'll tell you that like it extends linearly. But basically, if you have some decomposable K form, which is the wedge of K1 forms, and you're taking the inner product with another wedge of K forms, then this is defined to be the determinant of the matrix whose entries is the inner product we just defined of the forms alpha I and beta j. So you construct this matrix by taking inner products of forms alpha I and beta j, and then you take its determinant, and that gives you an inner product on the wedge K spaces. Okay. You can show, of course, this is a inner product. I'm not going to go through the details, but this will give us an inner product on all K forms. Okay, any questions? Okay. All right. Sorry, I'm like kind of speeding through all this, but I just want to like make sure that we can get to the main stuff. So okay. So now that we have this, we can also talk about most importantly, we're going to want to talk about oriented manifolds because we're going to want to do integrals and stuff. So on oriented manifolds, I think we've seen this before in one of Will's seminars. We have a choice of non-vanishing section of the top exterior power, so wedge n of t star m. So there's a non-vanishing section on this top exterior power of m, and that's basically what we call like a choice of orientation. Essentially, it's called like a volume form or an orientation form. So, and this is like a one-dimensional space. So we can also find an omega in these omega n of m that satisfies wedge n g omega omega equals 1. So now that we also have this metric on the top exterior power that we just defined, we can find a non-vanishing section which is not only non-vanishing but also has norm 1 under this metric, and this is what we'll call the volume form. And we'll usually denote it by d volt p or d volt g. It's the Riemannian volume form, and this is essentially the object that allows you to integrate on Riemannian manifolds. Integrate functions. Okay. Good. Okay, so now that we have that, there's an operation that we can define called the Hodge star. Okay, and the Hodge star is basically defined implicitly. We're going to define the Hodge star as a map that goes from wedge k. I'll just define it on any vector space for now, but later we'll take them to be tangent spaces. Minus k. So we know that, in general, wedge k of v and wedge n minus kv have the same dimension because of this combinatorial identity, n choose k equals n choose n minus k. So these in general should be isomorphic, but now actually we're going to show that we can construct a canonical isomorphism given this Riemannian data. And how are we going to do it? We define this implicit way of defining star beta by saying that whenever beta is a k-form, for all alpha n minus k forms, or n minus k, n minus k forms, we'll define this thing to be this alpha, beta, omega. Is this correct?
What is beta? Is it a K form or in minus K form?
Beta is the K form, yeah. Beta is the K form that's living in here.
Then shouldn't alpha be also K form?
No, but star beta is going to be...
N minus K, right?
Oh, yeah, alpha should be a K form, that's right. Yeah, that's right. Yeah, good. So the way that we're going to define this is that the star is defined sort of implicitly, but it's defined in the sense that like whenever you have k forms and you wedge them with star beta, this of course is going to be an n minus k form. This is a k form, so they'll wedge to something that lives in the top form. So it has to be, of course, proportional to our top form omega. and the proportionality constant has to be the inner product of those k-forms, which we also defined before by extending. Okay. You're still able to compute star beta because even though it's implicit, you can always compute this in a basis and calculate the components of star beta.
Can I ask a question?
Yeah.
For this part here, do you need compactness?
For this one?
Yeah. Like I can see, okay. I can see you can define this in general, like even if you don't have compactness. But I'm wondering, I don't do pure Riemann geometries, I don't remember this too much.
Yeah.
But would this d vol g also depend on the omega you choose? Or because if it's compact, then the top
Yeah.
homology is one-dimensional, so you have a canonical choice.
Yes.
But if it's not compact, like different omega should give you different d vols. Am I wrong about? Not sure.
If it's compact, the top cohomology is. What did you say exactly?
Is one-dimensional.
Is one-dimensional, yeah.
Just by Poincaré.
By Poincaré, yeah, right.
Assuming it's connected.
Yes. True. Yeah. So yeah, I think we do need compact. Because actually, technically speaking, you do have, even in the compact case, you have two choices here.
Yeah.
Because of like the sort of thing that's going on there with the equation. But yeah, I think we do need to assume compact. I think you're right. Yeah.
If it's not compact, what happens?
I think like this d vol, like you once you choose, you can choose different omegas and they're gonna give you different volume forms. So this d vol g would be d vol g comma omega or something. It would depend on which generator you choose, like for which directed, something like that. I'm not really sure. I'm not gonna lie.
There would be different non-vanishing sections. There would be many non-vanishing sections, many not the same non-vanishing sections, basically, that can give you different volume forms, I guess, in the non-compact case. Yeah, so, yeah, we're going to assume compact even for most of everything that's coming as well. So, yeah, I guess I haven't said explicitly yes, but let's assume compact for everything. Yes, thanks for that's good. That's a good good note. Okay. Good. Cool. So that's the Hodge star. Yeah. And just of course it's an isomorphism, and it's almost its own inverse. It squares to -1 to like if we call this star k. Star k squares to -1 to some power of -1 to some power, depending on k and minus k, and then the identity on k forms. Okay, so it's very close to being its own inverse. Okay. Actually, I guess this should be like star k star n minus k or something like that, right? Or
Yeah. Composed.
yeah, something like that. Okay. But yeah, generally we won't really write the k's and stuff. So, okay. So now, yeah. So you can also, of course, I wrote v here, but you're just gonna apply it to TPM for RPM, yeah. For
The last identity that you wrote, is that also true for pseudo-Riemannian case?
No, in this, so yeah, if you have a general metric of some signature, then you would add the signature there. So if you're, and this is like the determinant of, like, yeah, the determinant essentially, the signature of your thing. So if your thing is like minus plus plus plus, then this would be -1, and so on. If you had signature minus minus plus plus, then this would be +1, so on. So yeah, you can add that signature there.
What is the signature if it's, what is the signature for the minus plus plus?
Sorry?
What's the definition of the signature here?
For the signature, so whenever you have a non-degenerate quadratic form, you can always, there's this theorem that you can always put it into a form where it's like -1, 1, 1, 1, and some matrices here and here. I'm not sure what, I think it's, I think similarity or something like that. So you can always write it like this, where like, this matrix is the signature, and so the determinant of this matrix is the signature of that. So in the pseudo-Riemannian case, you have this signature, and then in the regular Riemannian metrics, they're just like that. You can think about it as choosing an orthonormal basis, essentially. Yeah.
Also, I retract my statement here, because since you said oriented, you're already fixing a non-vanishing section. So you already, it is canonical. I retract my previous statement.
Yeah. By saying oriented,
you're already fixing
fixing
choice of a generator, so you don't need compactness to do this.
Yeah, you choose one in one cohomology class, basically.
Yeah, you already fix a cohomology class.
Yeah.
If it's orientable, then you can have many choices. But if it's oriented, you already fixed one. So
right.
It's
Right.
canonical in this case. Okay.
Mm-hmm. But you still have the choice between plus and minus the d vol g. So that's always going to be there. Whereas, for example, like on a symplectic manifold, you actually only have one choice from the nth exterior power of the symplectic form.
Yeah.
Okay. Okay, good. So now I'm gonna show that I'm gonna define an inner product. I'm going to define an inner product, on K forms. Now, K forms not at a point, but rather smooth K forms. That'll take us to R. And I'm going to define it as alpha beta equals the integral over m alpha beta d vol p. Okay. And p here. Okay. So again, we define this inner product pointwise, but I'm going to now define an inner product sort of defined on smooth forms by doing it pointwise, multiplying by this volume form and integrating over the entire manifold.
Now you need compactness.
Now in compactness, yes. Very good. Exactly. Yeah.
Should I technically devote G sub P? Cause
Yeah, sure, yeah.
okay.
Yeah, sorry, like the notation won't be very,
Okay.
yeah.
But that's basically what you mean.
Yes.
Okay.
Good. Yeah, so now let's just assume compactness going forward, essentially. The non-compact cases will be weird. Maybe I'll talk a little bit about what happens, but I think I'll restrict myself to the compact case.
Schizophrenic rambling.
Yeah, we'll talk about that at the end, the schizophrenic ramblings. Okay. So, so now we have this. We can actually get the sort of like completion with respect to this inner product, get a Hilbert space. And we're going to call that L2 omega k. Okay. So these are just forms which have a finite norm. And now, technically speaking, it's a little bit weaker. Like, these things don't really have to be smooth and stuff like that, because they're not going to have to be. They can be not defined on the entire space. There's some measure stuff that's going on, but essentially this space omega k is dense in L2 omega k. Okay, so we can approximate things that live in here very well by smooth K forms. Okay, so essentially also moving forward, our forms will live in L2 omega k, but smooth K forms very generally will approximate these things, and so most things that we'll be talking about also will apply to K forms. Okay? Okay, so now we're going to show that the exterior derivative has an adjoint, a formal adjoint in L2 omega k. D, the map, so yeah, the map that goes from omega k to omega k plus 1 has a formal adjoint D star, which live, D star, which will be a map that takes us from k to k minus 1. And we'll find an explicit form for this, which was going to be minus 1 to some power, which I don't remember, and star d star. I think it's n plus k plus 1, but I'll double check that. Okay. So, yeah, so we're going to show that there's a formal adjoint for D, in the sense that, like, if I have D alpha with beta, then I can write this as alpha with D star beta. Okay. So technically speaking, I should be restricting to these spaces, and I think I might as well just write them. And actually, there's more subtlety even, because I should be talking about spaces of which alpha is square integrable, but also d alpha is square integrable. So, yeah, maybe I'll just write that here. You have H2 of omega k. Those are spaces, alpha and beta in L2 omega k, for which you have, alpha, just alpha in L2 omega k, for which alpha, d alpha, d alpha is also finite. This is H1. Okay. So this is called a Sobolev space. And this thing also has a norm, but I don't think we'll need that for now. But yeah, technically, we should be talking about forms that live in there. So yeah, these maps should technically be H1 and stuff. But again, like with density arguments and stuff, like you can also say things about what happens in smooth forms. So okay,
I mean, superscript 1, does that mean there's like HK as well?
Sorry?
What does that superscript denote?
The superscript means that basically, like, you have the first derivative is also square integrable.
Oh, so if we put 2, but that's just like 0.
For 2, in the case of here, you would ask for d alpha and d star alpha to both be square integrable as well.
I see.
And then for higher, there are sort of like things. I mean, usually you'll define these on functions, and then that way you just use gradients and stuff like that. But if you want the full details, you'll technically use a Levi-Civita connection or something, or a connection in general, and say that those you can take as many derivatives as you want. Okay. Yeah.
Does d alpha imply that alpha is square? Like that this is less than infinity, does that imply that alpha is also square integrable, or no?
Yeah, I'm asking alpha to be square integrable.
Oh yeah, my bad.
And then I'm also asking for d alpha.
Right.
Yeah. Yes.
That's both couple of conditions.
Yeah. Yeah. Okay, good. Any other questions? Okay. All right. So let's compute this formal adjoint. I actually did alpha with d beta, so let's just do that. Alpha with d beta. I should also say that this formula here, just using the formula for the star, you can also write it as the integral of alpha wedge star beta, just as forms. So that's also nice. Okay, so I'm going to use that to write this as the integral rem of alpha wedge d star beta. And now I'm going to basically.
Should we
Yes.
see star d beta?
Oh, thank you. Yes. Yes. Start the beta. Good. Yeah. Thanks. Okay. And so now I'm going to basically. What is? Oh no. Actually, I do want to actually do the alpha. Sorry, I want to do the alpha with beta. Sorry, guys. The alpha, which, sorry, beta. Okay, and then just a small aside here, that d of alpha wedge star beta is equal to d alpha wedge star beta plus minus 1 to the alpha alpha wedge d star beta. So I can, this is what we have, and I can solve for it in terms of that. If m is without boundary, the integral of the exact will vanish by Stokes' theorem. I'll talk a little bit about the manifold with boundary. That'll be of interest to us. But let's, for now, say that m is without boundary. Essentially, if m has boundary, you can also ask for a very specific kind of H1 space for which forms also vanish on the boundary of m. Okay? In which case that will vanish anyway because the forms restricted to the boundary will vanish. Alpha wedge star beta will vanish on the boundary. Okay. D, so what is this now? Minus 1 to the alpha alpha wedge d star beta. Okay, and then I'll use our formula for star squared to insert here. Yeah, and let's just say alpha is a k form here. So if alpha is a k form, then I have minus 1 to the k plus 1 alpha wedge. Here I'm going to insert star squared, but I also have to insert some minus sign, which is going to be, let's see, d star beta is a, if alpha is a k form, d star beta is a what? K plus 1 form?
Sorry, beta is the k plus 1 form. So if you use star,
then it's n minus k minus 1.
1.
So it's n minus k. Right? Oh no,
Yes.
we can see it from here
Yes,
because
yes.
it's just k plus 1. Yeah. Beta is k plus 1. Right? Because alpha is k. So the inner product
Yes.
has to live in the same space.
Yes, yes, yes.
So beta is k plus 1. So star beta
wait,
is.
no, alpha is k, so
Sorry?
No, you were right the first time, yeah.
no, if alpha is k, then d star beta has to be n minus k for it to be a top form. Right? Okay, beta is k plus 1, yes?
Yeah.
And d star beta is n minus k.
N minus k.
Exactly.
Okay.
Exactly.
Yes.
Yeah.
Yes.
Yeah.
Which is, yeah. So essentially, basically, this minus sign here will still be k n minus k.
Yes.
Because beta is n minus k. Yeah, star d star beta d star beta like this, and you can take this minus side, this whole minus stuff inside here, and then you can, as an exercise, show that that exponent is mod 2 equivalent to this thing here, if you want. Okay. But yeah, okay, I'll call that a proof there. I'm not going to waste time on minus powers if that's okay.
Question.
Yeah.
So the general product, inner product of alpha beta, that's defined as the second term, right?
Here.
Yeah, that's
Yeah.
So that's a definition.
It is definition, yeah.
Okay. But the third term is a theorem.
Well, it's just a consequence of the
Oh yeah.
of this
Okay.
equation here.
Okay.
So you can define it either which way,
Okay.
and both are the same.
I see. Okay, thanks.
Yeah. No problem. Okay. Good. Any questions? Any other questions? Sorry? Yeah.
Why is the integral of d alpha which star beta 0?
Why is the integral of which? Of this one?
Yeah.
Yeah, so Stokes' theorem says that on a manifold, well, in general, Stokes' theorem on a manifold with boundary says that the integral of d omega is equal to the integral over the boundary of omega pulled back to the boundary. And in the case that you don't have boundary, so this is an empty set, then this integral just vanishes. So, yeah. Whereas if we did have boundary here, then we can also do something where we like restrict this space to not only just forms, but forms whose pull back to the boundary vanishes, in which case this integral will also go away. Okay. So in both cases, they'll.
Are there other like interesting boundary conditions, or is that like the?
Yeah. Yeah, there are other interesting boundary conditions. Yeah, so this one would be a Dirichlet boundary condition, where you're asking for the forms to vanish on the boundary, but you can also ask for, you always have a sort of normal vector when you have a boundary defined everywhere, and you can ask for forms who, how does it go exactly? Forms whose, if you hook them with an n, or iota n or whatever people call it, it vanishes on the boundary. That would be something like a Neumann boundary condition. Okay, so like basically the derivative with respect to the normal vector of the form at the boundary vanishes. And yeah, you can ask for these boundary conditions, and I think in general, yeah. So this one is interesting because, well, they're both pretty interesting, but this one doesn't really give you new information on the cohomology side, whereas this one actually does. I'll talk about that a little bit later. But yeah, this is the only other one that I really know about. For Annabelle, yeah.
What do you write taking the derivative of your form with respect to the normal vector in our new language of forms?
Yeah, I'm gonna have to like.
Just
that makes sense.
flow through the normal vector.
Yeah, I think you just use the Lie derivative.
Okay, cool.
Because this part here is one of the terms. If you like percent magic department, this just tells you that.
Yeah, that's right.
Oh.
Yeah, I use Cortan's magic formula.
Yeah.
Yeah, that's right. Yeah, and then this vanishes for top forms, so then.
Yes.
Yeah.
Is that an L or an iota?
This should be Yoda. Yeah, it's like the
Oh, I see.
interior derivative.
Yeah. Okay.
Yeah.
Gotcha.
Yeah.
Okay, I have another question.
Yeah.
What is absolute value of alpha?
Where?
Absolute value of
That's
alpha.
the degree of alpha. So like which k?
Oh.
Yeah.
Okay, thanks.
Yeah. Okay. Good. All right. Good. So we proved that there's a formal adjoint, and when M is compact, and well, we're assuming M is compact. So when basically on this space L2 or H1 or whatever, this is actually just a real adjoint. I said formal adjoint because I was sort of like implicitly thinking about omega k, but it's actually just a real adjoint on the subleft spaces. You would have to worry about boundedness and stuff in general, but I think we're okay in terms of that. But now we can actually define a sort of very natural self-adjoint operator, the Hodge Laplacian. Which goes from omega k, L2 omega k into L2 omega k. I have to think about the spaces now properly. I think it's L2. We'll see. Maybe we'll come back and change that in a second. But it's just defined as no. I think you can define it in general there. It's just defined as d star plus d star e. Okay. So it's clear that this takes k forms and returns k forms because this increases degree and this lowers degree, and similarly there. And it's also self-adjoint. You can just take a star and this term will become this term and this term becomes this term. Okay. One thing we can immediately show, a couple of things about the Laplacian, is that now if we restrict to this H1 space that lives inside of L2, and we take delta omega omega in brackets, so this is a bit of a weird thing that we'll do in general, is that technically on H1 we might not be able to take delta because you might not have square integrable d stars. But actually we're not going to really need delta omega omega because we're sort of going to like implicitly use the fact that these are adjoints of each other and just move them over. So if you do that, for one term you get d omega, and for the other term you get d star omega, d star omega. And that's just from, you take this d star and you move it over, and you take this d and you move it over to get d star. Okay, so if you want to be fully correct, this only works for H2, but you can also just define this weakly by defining it like this. Okay, and it's clear that this is positive, okay, because I have integrals of things that are positive, and that tells me that delta is a sort of positive operator. Okay, and good. So delta is a positive operator, and it's also self-adjoint, as we said, because of the star thing. Okay, this is all good. Do we have questions? Are the people in Discord? Can you see the stream? Okay, I'll just assume yes.
See the stream.
Okay, thanks. Yeah, question?
I'm not immediately seeing the self-adjointness like up to a minus sign.
The self-adjointness?
Yeah, up to a minus sign.
So I mean, whenever you have an operator a star a plus a star is self-adjoint, because if you just take a star, you get a star plus a star a. Which is
but if we I understand now. But if we write it like that, we're basically doing a left and a right Hodge star on both sides, right? And then multiplying it by a negative to make it work out, right?
If you do what?
If we write it out in terms of Hodge stars.
Yeah.
So basically we're multiplying from the left and right by Hodge star. When we take the
you can substitute in this for the formula we found for star, and similarly to here. Yeah.
Right, okay.
What's the? I don't understand. What's the question?
It's resolved.
Okay.
Yeah.
Okay. Cool.
Thanks. Yeah.
Okay. Yeah. I mean, you can also show it just by like writing this and like moving things over twice, if you want, and showing that it's the same operator at the end. Okay. Good.
Nice.
So, We're going to be interested in a bunch of things about this Laplacian, but in general, it's not a bounded operator, which is really annoying because those are hard to deal with. So we're going to sort of do some juggling to, this eraser is really bad, to avoid the fact that it's not compact and work with something that's a compact operator. So because it's positive, the operator delta plus I, where I is the identity, 0 will not be in the spectrum of this operator. So the spectrum of course is the functional analysis spectrum. 0 is not going to be in the spectrum because delta is positive, so delta plus I, the eigenvalues have to at least be 1. Okay. So that means that we can actually sort of create an inverse for this thing. Okay, so basically the big theorem will be that delta plus I inverse, which will go from L2 omega k into H2 omega k. Because essentially if you think about delta, it takes H2 things to L2 things, and actually that'll be something that I'll talk about in a second, but this thing will go the other way. This thing will be a compact operator. I'll do a bit of the proof. It uses what's called elliptic regularity. Elliptic regularity, which is essentially that the space H2 omega k, which is forms on L2 omega k, like I was saying before, where alpha, d alpha is square integrable, and d star alpha is also square integrable. Oh, I forgot to mention something. That's okay. I think that can wait. Well, actually, maybe I'll interrupt this just quickly to say here. One thing that this implies is that basically this is 0 if and only if omega is closed and co-closed. Okay. So you can see that if this is 0, then these two will have to be 0, which means that d omega and d star omega have to both be 0. Okay? So it's equivalent to say that omega is harmonic. So harmonic means that its Laplacian vanishes, to saying that it's closed and co-closed. Okay? So essentially, we'll never really work with the Laplacian itself. And that's why, here I put quotes, because we'll just think about harmonic forms as being forms that are closed and co-closed at the same time. Any question?
How can delta plus I inverse be compact if it doesn't have 0 in its spectrum? Isn't that a theorem that compact operators have 0 in their spectrum?
They can have an accumulation at 0, right? Is that right?
Well, yeah, but the spectrum is compact, right? So it's also going to contain, it always has an accumulation point at 0, and sigma is compact, so it's going to also have 0, right?
Sigma is compact.
Or the spectrum is compact.
Yeah. Why does that mean it has to have 0?
Because then you just go towards 0, and it's also in the spectrum. Right? If the spectrum is compact. And it's an accumulation point at 0.
hold on. The
Major compact operators are never actually truly invertible, like maybe up to finite dimensions or something.
well, so this is not a compact operator from the space to itself, though, right? Is that like the thing that you're talking about?
Yeah, that's what I'm getting.
Yeah, it's from from one space to a different space, so it's kind of different, I think, right?
Yeah, no, that's a good point.
Yeah, but yeah. But yes, I think that I think it's still, yeah. That's a good question, though. I'm not sure. I'll have to think about that.
Why is it a different space? Why is it not L2 to L2? Because we defined that Laplacian from L2 to L2, right?
Should it from H2?
Yeah. Because like all these like things that we've proven so far, we've proven on like this theorem, for example, only holds for forms that are closed. Like I can actually take this integral,
Okay.
so it's only applies for like things that live in there. So yeah, we can only do this for H2 things. But it goes from L2 because of the following theorem, which says that elliptic regularity, which says that if you have U in L2 omega k and delta plus I, U equals F in L2 omega k, then U is actually in H2 omega k. And so this is all a theorem. And there exists C greater than 0 such that the norm of U, the H2 norm of U, is less than or equal to C, the L2 norm of F. Okay, so this is just a theorem of elliptic regularity. I'm not going to prove it, but it's a theorem that works for this Laplacian. It works for Laplacian, but also works for Laplacian psi, of course. What is the H2 norm? The H2 norm is just the norm of alpha, the regular L2 norm, plus the norm of d alpha, plus the norm of d star alpha. So it's just all of these norms added together. Okay. So that's the norm on this like subelliptic space. On H1 you also had a norm. H1 we said is ones where d alpha was integrable, and so we could define this norm. So in general you could define these sort of subelliptic norms. And this theorem tells us that the H2 norm is sort of like bounded above by the L2 norm of F. What does this mean for us? And yeah, so this sort of justifies why delta plus I inverse will go from L2 omega k into H2, because we have that U actually lands in H2 if these conditions are satisfied.
Can I ask a question?
Yes.
So this delta, is delta defined on H2 or L2, like the domain?
Delta?
Yeah.
The domain, yeah. So yeah, it's an unbounded operator. So technically speaking, its domain has to be a subset of L2 omega k. So yes, it's like that's why we're like technically everywhere we'll have to use H2. So yeah, its domain is not actually all of L2. Yeah. Is that good?
Yeah, my question is, okay, I'm not an analyst and I don't remember much of my functional analysis.
Same.
Let's talk about this elliptic regularity. How can I, if the domain it's not L2, does the fact that delta plus I U like for this to even be defined, all I need U to already be.
In H2. Well, so okay, hold on. So we could define, no, I think yeah, no, we can still define delta on L2, right? Just by yeah, is that right? Yeah, no. Oh yeah, you're right. Yeah. Okay. Yeah, I mean, okay, yeah, true. That's true. I think we just need U to be in H2 anyway. That doesn't really change much, though.
Yeah, I think the two like the important part is this last part,
Yeah.
right?
Yeah. I think we just need U to be in H2. Yeah, I think you're right. Yeah. But this can be in L2.
Yeah.
This actually, yeah. Yeah, good. Okay, yeah, thanks. Good. So, why is this good for us? Because essentially, now we have that U is delta plus I inverse F. And like if we apply that there, this tells us that U in the H2 norm is less than or equal to, and U is U is delta plus I inverse F, so delta plus I inverse in the H2 norm is less than or equal to F in the L2 norm. Okay, and so that completes that. C. Yeah. Okay, so that implies it's bounded in. Okay, and so that gives us that it's a compact. Sorry, it's bounded, and then we also need to show it's compact. It's compact because of another theorem. Sorry, it's not that. It's compact because we have an embedding of H2 omega k into L2 omega k, and another theorem tells it that this embedding is compact. It's a compact operator, and so now we can sort of apply delta plus I inverse. Yes, composed with this operation I. And this is an L2 to L2 map. So I think this is the idea, is that like sometimes you'll compose with this embedding, and then that way you end up in L2. But now this is bounded composed with compact, and so this is compact. Okay. This is called the relic Hodge. It tells you about how subload spaces embed into L2 spaces. Okay, but it's a compact, and then you have bounded with compact is compact. So this operator is compact. Okay. Okay. Sorry if I butchered that. My functional analysis is not so good. All right, any questions about that? Okay, good. So now we have a compact operator, delta plus I inverse. And so now, just from functional analysis, compact operators are very nice. Not only is it compact, it's also compact and self-adjoint, because delta is self-adjoint. So then actually we have the spectral theorem for compact self-adjoint operators. Okay. And basically this tells us that there is a basis of functions. There's a basis of functions, and again, there's sort of abuse here that like this actually means this composition where we embed H2k, H2 omega into L2. But yeah, I'll keep writing it like this if that's okay. So now we actually get a basis of functions phi k in L2 omega k, which are going to be eigenfunctions of this thing. So basically the spectral theorem tells us that there exists, the spectrum is basically just eigenvalues. Spec of delta plus I inverse is just a point spectrum, they're just eigenvalues. And that there is a basis of eigenfunctions that are orthonormal as well, or orthogonal in general, such that delta plus I inverse phi k equals lambda k phi k. Okay. Why is this good for us? Because actually now we can obtain that the Laplacian actually has a point spectrum by just moving things around. So I can multiply by delta plus I to get that phi k equals lambda k delta plus I phi k, and solve for delta phi k. And I get that it's equal to 1 minus lambda k over lambda k phi k. Okay. So now actually we've shown that the Laplacian has these eigenfunctions with these eigenvalues, and this is not going to be a problem here because we know 0 is not in the spectrum, so we can divide by lambda k. And further, because the spectrum of the Laplacian is positive, this thing here has to be positive. So this is positive. Okay, and then you can show that. Yeah. So 0 is not going to be in the. Oh no, 0 can be in the spectrum. 0 is in the spectrum, but actually these numbers are going to go towards infinity. So lambda k will go towards infinity as k goes to infinity, and that's because the spectrum of this thing can accumulate at 0, or will accumulate at 0. Okay.
Basel, can I ask something about that?
Yes.
So, like, I don't see like the full left of the board. You seem to say that like these 1 minus lambda k over lambda k are going to be positive. But if lambda k goes to infinity, won't they just become negative and stay there?
Sorry, not these lambda k's. Sorry, 1 minus lambda k over lambda k goes to infinity. Sorry. It's because yeah.
So all of the lambda k's are actually less than 1?
Yeah, they're between 0 and 1.
Okay.
Yeah. Yeah.
Thanks.
Yeah, no worries. Okay, any other questions? Yeah.
So what's the like range of for the spectrum of delta?
For the Laplacian, yeah, sorry. So yeah, I wrote lambda k because that's what we're going to be using, but maybe I'll write tilde for these lambdas.
Okay.
So, you know, these new lambdas, the eigenvalues of the Hodge Laplacian, basically you'll have 0 less than equal to lambda 0, tilde less than equal to lambda 1 tilde, and so on up to infinity. And you can have degeneracy, so you can have multiple eigenvalues which are the same, but they'll in general go on to infinity.
Can we call that unbounded?
It's unbounded, yeah. Well, it's unbounded because, like, you know, it can, yeah, it's unbounded in general. It's an unbounded operator, yeah. Yeah.
And but it's still point. The spectrum is pointless. That's a point spectrum.
Yes, on a compact manifold is very important.
On a compact.
On non-compact manifolds, a lot of the things that we did fail, and then they can have continuous spectrum.
Okay.
Yeah.
But no residue.
No residual spectrum for self-adjoint operators. Yeah. Good. My pages are out of order, sorry. I knew I should have ordered them. We did that.
A question to whoever's watching the thing. Can you see all the board?
Yeah, can you guys see the boards fine? I think it's like a little bit, maybe we need to push it back a little bit.
Because
Yeah, at the far right, I don't see.
Is that better?
Hold on, buffering. I think so.
Okay. Okay, good. Okay,
Yeah.
cool.
It's a little hard to read at the far right, just because like it's small over there, but I can see the whole board.
On that way.
Yeah.
Okay, I'll try to write it a little bit
Fine,
bigger
right.
over there. Okay. Okay, cool. All right, any questions about just this basic stuff? Okay, good. Good. So now we have that. So of course, you know, generally when people think about the Laplacian, they're just thinking about the scalar Laplacian. But of course, we recall that functions are zero forms. So actually, everything that we did also works for functions. Because functions are zero forms, and you can retrieve your regular Laplacian that you know and love just by restricting everything that we've done here to zero forms. So on functions, basically, you can show that delta f on a Riemannian manifold is. I didn't actually write this in my notes, but Gij 1 over. Actually, I'll just write it like this: it's Gij delta Dij f. Yeah, let's just write it like this and hope that everyone is okay with the. Technically, you don't really need to. You don't really need this form of it. Like, I don't really need a connection to define all this stuff. You can actually just define this as you know, GKL divided by 2 DL, whatever, the usual thing. So, because everything we did here didn't actually introduce a connection, so I didn't actually have to use a connection to get that thing. But this thing is just something that involves G and its derivatives. And so just on functions, you actually just get the usual Laplacian. If your space is flat, then you just end up getting like that usual like second derivative thing. Yeah.
I've never seen it partial with two indices.
Oh, sorry. Yeah.
What is that?
That's just partial I, partial J.
Okay.
Yeah.
Okay.
Yeah.
And I think if you define that, like the symbols like this, that you are defining the retreated connection.
Yes. Yeah.
Technically, so.
Yeah. True. It is. But you can actually also write this. I didn't write it in my thing, so I'm like kind of, you know, I think it's like 1 over root determinant G, D I G I J, root determinant G, G I J, partial JF. Okay, I can also write it like this, I think. Okay, and so that way you don't even need to write this down at all. So, but yeah, they're equivalent. You can one can check they're equivalent. The question,
Sorry,
yeah.
Are you saying the lambda I tildes are the 1 minus lambda I over lambda?
Yeah, these.
I see. Yeah.
Yeah. So the spectrum of the Laplacian, the point spectrum of the Laplacian. Okay, good. So yeah, so that's just the regular Laplacian that you know. Regular manifolds. And so part of the spectrum, most of the spectrum that people are interested in are just the spectrum of the functions. But in general, we've shown that like you can do it for forms as well. Okay, so now we have this like spectrum of the Laplacian. There's a bunch of questions that one can ask, which is like some questions is like how fast do these grow, because they go to infinity. How fast do these grow? Another question is, what can the spectrum tell us about the Riemannian manifold? What can the spectrum say about Mg? Okay. Can it give us any interesting information? And if I have two manifolds, two Riemannian manifolds that are isometric, isospectral, let's just say Mg, M prime, and G prime, isospectral. So isospectral means they have the same spectrum of the Laplacian, the Hodge Laplacian. If I have two isospectral MGs, are they isometric? What is isometric? Isometric just means that there's a invertible, in this case diffeomorphism, since they're smooth. You have a diffeomorphism between them that preserves the metrics. So the metrics are pullbacks of each other under those diffeomorphisms. Okay, so we'll answer all of these questions in a little bit, but first we're going to talk about Hodge stuff. So before we get into that, are there any questions? How long have they been going? Is it 1 hour, I think?
5:30.
Yeah. Okay, I'll try to do this quickly. Yeah.
Another question would be, how does the entire talk generalize for the pseudo-Riemannian case?
How does everything generalize for the pseudo-Riemannian? Yeah, that's a great question. That's not very easy.
Yeah.
Yeah. So, but yeah, some things, something kind of work out because, so in general, the spectrum of the Laplacian will still tell you something about the spectrum of the wave equation, because you can always separate variables, separate out the time variable, and actually what you end up solving, like if you have a wave equation. I should say something. Is that this is actually negative Laplacian that you actually know. The Laplacian that I've worked with here, because the spectrum here is strictly positive, but the Laplacian that you usually know is actually negative definite. It has a negative spectrum. So that's why there's a plus here. But if you have something like this, you can actually always separate out the time variable and obtain an eigenvalue equation for delta. Okay, so yeah, question?
Can I just ask what's going on with this gamma?
The gamma symbols? Yeah, you kind of forget about the gamma thing and just like take this thing, if that's okay. I kind of wrote it out because I wasn't sure if this was right, but I think this is the correct form.
It seems correct to me.
Yeah. But generally, this thing is just like some. It's another way of like once you expand this thing, it's an equivalent way of doing it. But also like it's something related to the Levi-Civita connection of the Christoffel symbols or the. Okay. So I haven't really defined them, but you can just take this one if that's okay.
Sounds good.
Okay. Go. Yeah. Another question.
Follow up for the last question I asked. So you said because it's negative, the one that we know. That's why there's a plus there when you separate the time and delta, right?
Yeah, the delta here is positive definite. It's
Yeah.
negative of the usual Laplacian that you know. So yeah.
Okay. Can you always do this separation, even though your like Christoffel symbols in GR they mix the time and space component?
No, yeah, you can't always do it. you can do it in what we'd call like globally hyperbolic spacetimes, or something like that. But no, in general, you won't be always able to do it. But in those spacetimes which separate up to like something like this, or if you're within a vicinity of a Cauchy surface or something, then maybe you can be able to do it. Yeah.
So in Minkowski, you can always do this separation.
Oh yeah, sure. In Minkowski, it's easy.
Okay, but in general GR, you can't.
No.
Okay. Thanks.
It is because you don't have a preferred time direction, right? That's global hyperbolic gives you a foliation where you can define at the time.
Yeah.
That makes sense.
That's
That
right.
makes sense.
Yeah.
Okay, thanks.
Yeah, no problem. Okay, good. So let's do some homology, cohomology stuff. So we know we have this D operator, which gives us this nice complex on the omegas. But now we also have D star, which sort of goes the opposite direction. So it defines a chain complex. On the same space. And we saw that the kernel of delta, if we restrict it to H2 at least, that the kernel of delta is forms which are closed and co-closed. Okay, so omega in H2 such that, sorry, there's going to be a lot of spaces called H now, but this H2 is the Sobolev space, okay? So, good. So, okay, so that's the kernel of delta. Now, this is a subspace in L2 omega k. Okay, and that means that L2 omega k can decompose into Kerr delta plus the complement, orthogonal complement. Again, we have inner products, so we can do orthogonal complements. So we can do the space. And of course, this is finite dimensional. Did we say why it's finite dimensional? It's finite dimensional because from before, each of the lambda k's, not the tildes, each of the lambda k's has an eigenspace which is finite dimensional. That's just from the theory of compact bounded operators. Okay, so each kernel of delta has a finite dimensional is a finite dimensional space. Okay, so now we want to understand this space, and to do that, we can define this operator the orthogonal projection onto the space of harmonic forms. So I'm going to call this HK, just so we can have more spaces called HK. But HK is the space of harmonic forms, so the forms that vanish under delta, and I'm going to define this another H.
But don't we also have the cohomology as well?
Oh yeah.
Oh my.
But it's okay. We'll see that everything is well defined. All the H's will be the same. I have a projection operator from L2 omega k onto curly HK. which is just the orthogonal projection. Okay, we have a space that decomposes into two components. I can just create an orthogonal projector. Yeah, question?
Okay.
Yeah.
You said that kernel of delta is finite dimensional.
Yes.
Can you say why that is again?
So if you remember, we had that delta plus I inverse, which we showed as compact.
Yeah.
And it had these eigenvalues lambda k.
Uh-huh.
And then we constructed the eigenvalues of delta from these, right? And essentially, each of these eigenvalues has a finite dimensional eigenspace by the theory of compact bounded operators. And we showed that the eigenfunctions of delta, or at least the eigenfunctions of this guy, were eigenfunctions of delta with with 1 minus lambda k over lambda k.
So are we looking for like eigenvalue 1 or something, and then that's going to give us eigenvalue 0 from delta?
Eigenvalue 1.
Like this is not delta, right? We're looking at the kernel of delta, not the kernel of delta plus I inverse. What's going on there? I guess I'm just confused about that.
Oh, why the kernel of delta? Yeah, the kernel of delta is I see what you're saying.
I think, isn't the kernel of delta the one eigenspace of
It's-
delta plus I?
That's what
It's
I
the
was
one
asking.
eigenspace. Yeah,
This
yeah,
is the
thank you.
inverse, right? Do we know that delta plus I is also compact? Because then that would make sense, but...
Hmm.
No, delta plus I doesn't have to be compact, right? Oh, why do you need delta plus I to be compact?
Well, because we're if the kernel of delta would be like like Will said, the one eigenspace of delta plus I, right? Because we're like subtracting away an I from delta plus I, so you just get delta.
Yeah. Good question. So yeah, the kernel of delta is the one eigenspace. So why is that a problem? It's the one eigenspace. It's the
But it's the one. Sorry.
Yeah,
It's
no,
the
go
one
for it.
eigenspace of delta plus I, not delta plus I inverse, right? Or is it?
No, delta plus I inverse.
Why is that?
Because the eigenvalues that we constructed, like, were eigenvalues of delta plus I inverse. And then we got the eigenvalues of delta. Like, these were the eigenvalues of delta, where these are the eigenvalues of delta plus I inverse. So if you have lambda k equals 1 for this operator, then we get 0 here,
Okay, fair enough. Yeah.
right? Yeah. So it's just the one eigenspace, and so yes, it's finite dimensional. Yeah.
What is the one eigenspace?
The one corresponding to the eigenvalue 1 of delta plus I inverse, which is 0,
Yeah.
of course, for,
Yes.
for delta, so that's why it's the kernel of
Okay.
delta. Yeah. Okay. Good. I mean, we'll also show now that it's finite dimensional just in a second, but it's also finite dimensional because of the reshutter there. I think, at least again, my functional analysis is very not on par right now. So, okay. So we have this orthogonal projector, which is just the projection onto the kernel delta. And so we have basically that any form. So how can I say this? So essentially, we can find on this space on current delta perp, we can find an inverse for delta. Okay, because we don't have 0 now, and essentially, so we can define this G, which goes from current delta perp into L2 to be just the inverse of delta. The identity on current delta perp. Okay, and we can extend this to all of L2 by just defining the action of G on anything like in kernel, like if I had omega in HK, which is the kernel of delta, then just define G omega to be 0. Okay, so we can extend its action to the whole space by just defining it on harmonic forms to be 0. And now essentially what we have is a G on the entire space which satisfies delta G omega, or let's just say delta G equals identity minus H. So essentially it's invertible. This matrix is like, you can think about it as like, if we're thinking about matrices, like 0 on the Kerr delta, and then 1 here on the HK perp space. Okay, so it's invertible. You know, this is what it means to be invertible just on this space here. Okay, and the action is 0 on harmonic forms. So this is what we call the Green's operator. And why is this good? Because now take any form in L2 omega k, we know that we can write it as delta G omega plus H omega. That's just by using that 1 is equal to H plus delta G. And what does this give us? This gives us D star G omega plus D star D G omega plus H omega. So this by definition is harmonic because it's the projection onto the harmonic subspace. This here is in the image of D star. Okay. So it's coexact, and this here is exact. Okay, so we've sort of found a way to decompose any L2 omega k form into a harmonic form, coexact, and exact form. Okay, and I can write explicitly here that these. And now if we want to show that this is actually like a direct sum, we just need to show that these two spaces are orthogonal. And that's pretty easy. Because if you have a form which is exact, and you take the inner product which is with a form that's coexact, and you just use the just bring this adjoint over, and this is of course 0. Okay, so those two spaces are also their intersection is 0. Okay, so we actually have a decomposition. L2 omega k equals harmonic forms plus exact plus coexact. Okay. Good. Yeah, question?
Stupid question, but what's H, fancy H of the...
Yeah, curly H is harmonic forms. Kernel of delta.
The one on the right, the kernel,
This one?
above that.
This one?
Right.
This
to the
H?
right.
That's this map.
No, to the right of that.
Which one?
In the matrix.
HK is delta perp. Sorry.
Yeah.
It's just the identity, like this is 0 on, on HK, and then this is 1 on the complement.
Right.
I was just describing this matrix here.
I see.
like h is the projection onto the harmonic forms, and 1 minus h is the projection onto whatever is remaining, right?
Right.
Okay. Let me know if you have any more questions.
Okay. Thanks.
Any other questions as well? Okay, so what does this mean? So now actually this is great because now we can show something very cool, which is that the space of harmonic forms is actually the same as the de Rham cohomology. Okay, so how can we show that? We can define a map phi from the space of harmonic forms into de Rham cohomology. And how do we do this? We just take any harmonic form and we send it to its representative in HK. That's because remember that harmonic forms are exact, so we can just send it to its representative in cohomology. And now we'll show that this is an isomorphism. So I've been erasing this board, but there's another board behind it that I keep forgetting about. So, yeah, every omega we can decompose into h omega plus d alpha plus d star beta. That's that Hodge decomposition that we just made. And now we know that d omega is 0 because we're talking about the decomposition of what are we doing exactly here? Sorry, 1 second. Yeah, sorry. Take just omega to be any closed form. Omega closed. Okay, so d omega is 0. Any harmonic form is closed, so that'll be 0. This will be 0 because d squared is 0. So this will tell us that for any closed form, this last term is also closed.
So what was h omega 0?
Where?
H omega, you said it's 0. Why?
D of h omega is 0 because because this is a harmonic form. Harmonic forms are closed.
Yes.
Okay.
Yeah. Okay. Thanks.
Yeah. No. Okay, so we have that d star beta is also closed. And of course, d star beta is also co-closed because if you take d star of d star, you get 0.
Yes.
But that implies that beta is harmonic because it's closed and co-closed. Okay. So, but if beta is harmonic, then like this decomposition, by uniqueness of the decomposition, because it's a direct sum, beta just has to be 0. Okay. By the d star, yeah, d star beta is harmonic.
Yeah.
Sorry.
Not beta, right?
D star beta.
D star beta. Yeah.
Yeah.
Okay. Phew.
D star beta is harmonic because
Yes.
because
Because
d of d star beta is 0, but of course d star of d star beta is also 0, so d star beta is harmonic. But then by uniqueness of decomposition, this is the harmonic part, so then this has to be 0 because they intersect to 0, those two spaces. Okay, because it's a direct sum. What we showed you. D star beta is 0.
Yes.
Okay.
Okay. Thank you.
Okay, so essentially for any closed form, the Hodge decomposition takes this form, okay, which tells us that the difference between omega and h omega is exact. And that tells us that in cohomology, omega and h omega are the same. Okay, so and further, we can actually, so this basically tells us that we have harmonic forms. We can always find a harmonic form in the cohomologies, but they're actually a unique one. How do we show that it's unique? Is because we can actually invert this mapping to go from the de Rham cohomology into harmonic forms by taking any closed form in the de Rham cohomology, any representative closed form, and just mapping it to H omega. And this is going to be well defined regardless of the representative, because if you have omega and omega prime in the same class, then H omega prime equals H omega plus H of d alpha. But d alpha is in the image of d, so by that decomposition, its projection is just going to be 0. So this is 0. So we have that H omega prime equals H omega, and so this map is well defined. Okay, and so this actually tells us that there's a unique harmonic representative in each de Rham class. Okay, so that's the Hodge theorem. That every de Rham class has a unique representative, which is a harmonic form of degree k. Okay, and that tells us that these two spaces are isomorphic.
Does this still rely on our manifold being compact?
Yes, absolutely. Need compact manifold, yes.
What's the definition of these representative de Rham classes?
Oh, okay, yeah. So the de Rham cohomology is the image.
The kernel.
Sorry. The kernel of dk
modded out by the image.
mod the image of
dk minus 1.
dk minus 1. So any omega. So the relation that you get here is that like two forms are equivalent if their difference is in here,
Yes.
right?
Yes.
Which means that their difference is exact.
Yes.
So what I showed here is that if you have two forms that are in the same class, then h of those two are the same, which basically means that this definition of this function doesn't depend on which representative you take of the class, because here I'm removing, like I'm picking an omega where I have a class, so it has to be well defined.
Yeah. And this one question is, what's the definition of a representative of a class?
So the class is just all the things, like, you know, it's just an element. A class is just an element of the space, right? One element of the space. But every element of this space is a set of equivalents, like a set of equivalent omegas.
I see.
Okay, so does that make sense?
Yeah, and you're just picking one of them.
You're picking one of them.
Okay.
Yeah.
Thank you.
No problem. Okay. Any other questions? Yeah. So okay. So this decomposition is sort of on L2 omega k, but like we said before, omega k is dense in the space. So essentially, like, you can approximate each of these components by their respective thing in omega k. So you actually also have sort of this thing also working on omega k. Okay, but the technical theorem, if you want to be rigorous, it's on L2 omega k, I believe. Okay. Yeah.
True that on omega k you just have like the same decomposition where each vector is intersected with omega k.
Intersected with
So
omega.
if we intersect this, like omega k is L2 omega k intersected with omega.
Intersected with omega k. That's
so
right.
The omega k just distributed to this sum, right?
Yeah, very good. Yeah, yeah. You just intersect everything with omega k. Exactly. Yeah, thank you. That's right. Okay, good. So that's the cohomology stuff. Good. Okay, now I'm going to go back to the questions. I just wanted to get that done with. Well, 6. Yeah, I might have to wrap up then, but we didn't even get to the spectral geometry. Okay, I'll try to speed through this. Okay, so I'll speed through this just so that we...
Are we on part 3?
Yeah. Well, we're part 4 now.
Oh, we're 4. Okay.
Yeah.
Okay. Nice.
Yeah. Sorry, I'll try to speed through this. We asked some questions before, which were like, how fast do these grow? How fast do the... I called them lambda k tilde, but forgive me if I just call them lambda k now. The eigenvalues of the Hodge Laplacian, how fast do they grow? Okay. I had the sort of like proof of this here, but I think I'm just going to have to skip it. But if anyone wants to like look over that, I'm happy to go over it with you. But Weil's law says that if we consider this so-called eigenvalue counting function, which is the number of eigenvalues lambda k in the spectrum, such that lambda k is less than or equal to lambda. And I write number here instead of set size because there can be multiplicity, and so like we want to count with multiplicity rather than set size. Okay, so the number of eigenvalues in the spectrum that are less than delta, Weil wrote a sort of asymptotic relation that says something about that. He said that this is equal to omega n, volume of omega divided by 2 pi to the n. That's on a manifold omega without boundary. If you have boundary, there's even and I'll define what omega n is in a second. If you have boundary, you also have an extra term. Volume of the boundary for 2 pi to the n minus 1. Oh, sorry, lambda to the n over 2, of course, very important. Lambda to the n minus 1 over 2. Plus, but in terms of smaller order. Little o lambda n minus 1. So what is omega n? That's just the volume of the n ball. Okay, you can express it in terms of the gamma function and stuff like that. But we have this, okay, and yeah, this is only if you have a manifold with boundary. We didn't really talk too much about manifolds with boundary, but actually, if you do manifolds with boundary, an interesting thing that you get here is if you impose the boundary conditions that the forms vanish on the boundary, then you actually get the relative cohomologies between omega and its boundary. So there's also like that kind of theorem there. But yeah, on manifolds with boundary, you also get this sort of growth law that this counting function grows like n over 2, and the boundary terms also matter, and they go like n minus 1. This is really nice because it sort of tells us that you can't just give me any set of numbers and expect it to be like a spectrum of a Laplacian. A spectrum of a Laplacian has to grow in a very specific way, which is like this. Yeah, question?
Sorry, what is this squiggle? Is that proportionality?
Which squiggle?
The
Oh, this is asymptotic. So like their ratio as lambda goes to infinity is 1. Okay, so this function, like divided by this stuff,
Yeah.
forgetting about this, I could just erase this. This function divided by this function as lambda goes to infinity, the limit is 1. So they're asymptotic. So it's how this is like how this grows, essentially. And this is the first order correction term.
What's the point of having the 2 pi at the end then? Is that
Well, if you didn't have it, because
one.
this, like it wouldn't be 1, right?
Oh, yeah, it's a normalization.
Yeah.
Right, okay. Makes sense.
Yeah.
Isn't the volume of the omega manifold a n form?
No, the volume of omega is just the integral of d vol.
Okay. Right. You're integrated, right? I confused it with the d-vol. Okay.
Yeah. And again, compact, everything compact, so that's finite.
Yes. Okay. Thank you.
Yeah. Okay. So yeah, this is a long proof. I'm not going to do it now, but it involves heap kernels and things of that sort.
I have a question.
Yes.
So this one you get for this boundary thing, you use the Dirichlet boundary condition.
Yeah.
Can you have a similar one if you use the Neumann?
With Neumann, so yeah, good. With Neumann, this just ends up giving you regular cohomology, and here you end up getting close. So yeah, it's interesting. I'll show you a quick example to see why that is. Just by talking about like how this works on R2, let's say. And that'll also show us how this whole story has a very interesting connection to number theory. The schizo ramblings at the beginning. So on two dimensions, I'm sure you've all solved the Laplace equation before. Okay, we get this lattice. The eigenvalues in 2 dimensions of just the regular Laplace, Laplace operator f equals lambda f. You find that lambda depends on 2 numbers, and so I should say my domain here is just the square. I'm solving like, for example, in quantum mechanics, you solve like the particle in a square box. And this has, let's do 0L. So it's a box with side length L, and it needs to be a pi squared, I think, right? Okay, so those are the eigenvalues. And the counting function is going to be the size of this set. 2 numbers. So again, for Dirichlet boundary conditions, these numbers have to be 1, 2, etc. But for Neumann, you actually include 0. Because basically the eigenfunctions for Dirichlet are like sine m pi x over L, sine m pi x over L. But for Neumann, they're cos and cos. And so when you apply the boundary conditions, you actually end up getting 0 as well for the Neumann ones. So let's do the Dirichlet spectrum though. For the Dirichlet spectrum, we have that these are in n squared, and we need n squared plus m squared to be less than or equal to lambda L squared by pi squared. Okay, and you're asking the question essentially, if I have a circle of some radius, how many grid points? In this case, we're not including these grid points that are on the lines here, but how many points are inside of here? And the way that we can see that is sort of by like thinking of the number of points as being these squares, like these squares. Okay. throughout. And so basically, like, the number is actually kind of approximating the area, okay, of this quarter circle in this case. And there's a correction term because I have sort of this extra, like, little bits going out from the squares. Okay, and we can kind of see that that's going to be related to the length, the arc length of this circle, which is why you get that extra correction term of the arc length there. And so, yeah, and the scaling is going to be like lambda, because so this is like, this is the this is r squared, right? This is the radius of the circle squared, and so what's the area of the circle is pi r squared over 4, which is going to be lambda L squared over 4 pi squared. Okay, and you can see that that's like what you would get as the first, as the first term there. Omega n is the one. Sorry, just
Yeah.
right here. Yeah, omega n is the one. So actually, we could just suggestively write it like this, where pi here is the omega 2, the area of the one disk, the 2 disk, the area of the disk, basically. And yeah, everything else matches. And the correction term comes proportional to the length of the boundary. I won't really do that, but that's kind of just how you see this, at least for this domain, which is like 0L, 0L. The general thing is more complicated. You need to do heat kernels and things like that. But yeah, there's a lot more interesting stuff, and there's a connection to number theory, where here, when you're counting these, you want to ask, like, how many eigen values, how many integers do I have that add up to this, squares add up to this number. This is just a number theory problem that you could solve with a Dirichlet character. And there's a whole interesting thing there, and there's a sort of connection with this here, and in general there's like a whole bunch of stuff that is like number theory related. But that's the first question. I won't really go too much longer, but essentially this other question was, what can we tell about the manifolds? And what we can tell about the manifolds, we've seen that we can kind of tell the volume and the volume of the boundary. So if two manifolds have the same spectrum, the volume of their boundaries and their volume have to be the same. Further, their dimension has to be the same. Probably this first is actually, the dimensions have to be the same. And another thing that has to be the same is that the integral of the scalar curvature has to be the same. So these are sort of what we call spectral invariants. Okay, so if two manifolds have the same spectrum, essentially, without going too much in detail, you can always define this function, theta function, or heat kernel trace, or partition function, whatever you want to call it. And this is just completely determined by the lambda i's, and this can be expanded on a manifold as a series, and these will show up in the series of this function. I won't go into it too much so I don't take up a lot of time, but you can ask me about it. And then basically these are all spectral invariants. So if two manifolds have the same spectrum, they have the same z, and therefore they have the same spectral invariance. But are two manifolds isometric if they have the same spectrum? The answer is no. So you can have manifolds which are isospectral, so they have the same spectrum, but they're not isometric as Riemannian manifolds. Milner gave an example in 1964 of two tori, well, like two spaces, basically. Like you take R16 and you quotient out by some lattice, E8, E8, and you take R16 and you quotient out by the other unimodular lattice in 16 dimensions. And was there a question? No.
I was just thinking this is a classical Milner thing to do.
Oh yeah.
Just come up with like a crazy example that just works.
Yeah, that's right, exactly.
For like profound reasons.
This is crazy. I wish I had time to talk more about this. But essentially, you have two lattices in 16 dimensions, which are what are called unimodular, and these two spaces actually have the same spectrum. The spectrum in this case is very simple to compute for these lattices, but they're actually, you can show that they're not isometric for a very, very simple reason, which is that like the way you construct these as Riemannian manifolds is that you just ask for this projection map to be an isometry, and that's just how you put these with their respective structure. And so, like, if these spaces were isometric, then you would actually end up getting a lift to an isometry of R16 that sends this lattice to this lattice. But actually, people knew that there are vectors in here that had norm, that no such vector had that norm in this space. So there is no such isometry which takes you from R16 to R16 such that these two lattices are sent to each other. So therefore, they're not isometric. But they are isospectral. Again, it's very simple. Technically, it's very simple, the computation, but you have to know a little bit about lattice theory. And yeah, use modular forms and blah, blah, blah. So yeah.
Is E8 different from the exceptional mean group?
E8 is the lattice E8, which is, it's the root system for the Lie algebra E8. Yeah.
Okay.
Yeah, so it's the lattice. The lattice came first, then the Lie groups.
Okay.
Yeah.
Is that just
Question.
is it the same thing as D16, just the lattice for the dihedral group, or what is that?
No. Yeah. So, no. I'll just say no.
Okay.
It's a lattice in 16 dimensions. That's like basically like you take all vectors which have a sum that is even, and also
Sum that's even?
Yeah.
Makes no sense.
a sum that's even. So like you have, you obviously have Z16 that's sitting inside of R16, right?
Okay.
Right. So you start you're starting your lattice by saying, take numbers in Z16, who you have 16 numbers, right?
Oh, it's sum that is even.
The sum of them has to be.
Subset of Z16.
Yes.
Okay.
Their sum has to be even.
Yeah.
And further, you also it's hard to define. So basically, it's Z16 plus union Z plus 1/2 to the 16. And you also ask for the sum to be even. Okay.
What does sum mean here?
The sum of the components of each of these guys.
Oh, you're summing component-wise. Okay.
Okay, so that's what this says. E8 is the same thing, just 8.
It's the same thing as 8.
Yeah.
Okay,
And
sure.
yeah.
Okay.
Again, yeah. If you guys want to go into more detail, I can do it, but I don't know how much time you guys have.
We can reserve it for another day.
Okay. Cool. Good. I think that's probably all I have to say, other than like, if you come with a spectrum that's, this is probably like a fourth unasked question, is if I come with a spectrum that's satisfying Weil's law, i.e. grows in that specific way that we said before, is there a manifold for which the Laplacian has that spectrum? And it is completely unknown, but essentially the way people will try to do this is by working with non-commutative geometry. Okay, so non-commutative geometry stems from the idea that like the spectrum of the Laplacian can't retrieve the geometry, which is what we saw, but Kahn found out that you have three things. If you have an algebra of functions, a Hilbert space, an algebra of operators, a Hilbert space, and an operator, an elliptic operator, let's say something like the Dirac operator, something you would call the Dirac operator, this spectral triple can actually retrieve a geometry. Okay, so if you have these three things, you can actually end up getting mg back completely. But if you start with these three things, you're actually not guaranteed to get a regular manifold. If this is just an algebra and this is just a Hilbert space and this is just some elliptic operator, you're not actually guaranteed to end up in a regular Riemannian manifold. In general, you can end up in what's called a non-commutative space if this algebra is not commutative. If this algebra is commutative, then yes, you end up getting a Riemannian manifold. But if this algebra is not commutative, then that's what defines a non-commutative geometry. And the question is whether any spectrum that has this Weil law type spectrum, if that corresponds to some non-commutative space, and that's ongoing area of research. Okay, I think that should be all that I should say at the moment. So, thank you. Thanks. Yeah.
About this last thing.
Yeah.
What is okay? So you have this triple.
Yeah.
Does the algebra and the Hilbert space have to be related somehow?
Yeah, you have to have an action
Okay.
of the algebra onto the Hilbert space. Yeah, like a representation. Yeah.
Okay.
Yeah.
Think about it.
And then this D will be an operator that acts on this Hilbert space also.
So like an element of A, or
Not necessarily, I think, because it's again not compact. And usually we want to think of these as compact operators.
Is it unique, this construct? Like you get a unique one, or can you have many?
Yeah, you get a unique one.
Oh.
Yeah, so given the Dirac operator, a Hilbert space, and the algebra of functions, uniquely gives you your Riemannian manifold back.
And what do you mean by non-commutative geometry?
So if you retrieve, if you take this to be the algebra of functions, this will be a commutative algebra, and so that way you actually just end up in a space here, just mg. So technically, this algebra of functions, it should be functions on, because this Hilbert space will be of spinors, because this Dirac operator has to act on it. This algebra will be, let me think, the space of functions, yeah, just the space of functions on your manifold. And if it's commutative, then you just end up getting your Riemannian manifold mg. But if it's not commutative, then you don't end up getting mg, because obviously this, any Riemannian manifold functions, algebra of functions is commutative. So by taking this algebra to be non-commutative is how you get the interesting non-commutative spaces in some sense.
Out of curiosity, I guess by algebra functions it means like the smooth functions.
The smooth functions,
If
yes.
I take polynomial, do you get a scheme instead, or like depending on which family?
I have a feeling that you could do something like that. But
I'm just shocked that you get like smoothness. I mean, that's quite shocking.
it is quite shocking. But you do ask for a lot of things here. So there's somewhat of like a redeeming factor there. So
Probably the elliptic operator.
take care.
Maybe in the elliptic operator there's some smoothness going on.
Yeah, here we already know that there's some invariant things going on. Even though I only looked at the Laplacian, but the spectrum of the Dirac operator also has, a lot of interesting theory that's very similar. And so, like, we've already, retrieved quite a bit of information, the volume and blah, 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 all this stuff. So then basically what it's saying is that the remaining information lives in those two things. Again, I'm not an expert on non-commutative geometry by any means, but that's all I know. Yeah.
So how does the entire talk generalize for the
Yeah, it doesn't. I don't think it does. It's hard. Yeah, I don't know. The true answer is I don't know. Yeah. But I told you, what I told you before about the wave operator. So,
Yep.
yeah.
Are those still in spectral invariant in the pseudo-Riemannian case?
Well, I don't know if we even have spectral invariance in the Riemannian case.
What does the pseudo-Riemannian volume look like?
Exactly, right?
Like, is that even a thing?
You do.
Yeah. I mean, you did in
Let me think. Yeah, well, the only thing you needed for the volume form is you just needed a non-degenerate form. Yeah, so I think you can still define the volume.
Yeah.
But it doesn't really, it's not really like the volume, right? But it's a measure. It's a measure.
It's still a measure. Of course.
Yeah, although actually it's not a measure because...
the negative, right.
well, no, it's a measure. It's a measure. But you have some non-trivial spaces like the light-like cones and stuff that have measure 0.
Yeah.
Anyway, it's really weird. Yeah.
And the sub-additivity is probably like now something modified. But
Yeah. Yeah. Yeah.
Some generalized measure, but sure, okay.
Yeah.
But
Again, I don't know how this fully generalizes to them.
Right.
But again, like, like the spectrum, like I said, like you can always, like on a globally hyperbolic space-time, you can do separation of variables. Or even like, like if you're doing GR, there's this thing called the ADM formalism where you do treat the space-time as being globally hyperbolic, and there's a way of splitting up the metric, and so on, things like that. There.
How do you say your manifold is globally hyperbolic? In GR, if it's like SR, I understand because that's what it is, right?
Yeah.
Which
There's like a requirement, like you ask that there is a inextendable geodesic or something like that. I don't remember exactly what it is, but there's this ADM formula. Again, I don't remember too much, but there's this ADM formalism in GR where like you can write any metric in a specific way. And you can, like, there are many functions, and one of them is like the metric on the spatial slice.
Yes, exactly.
And one of them is this what's called lapse function, and then you also have what's called a shift vector. I forget, but there's a term that mixes dt and dxi.
Yeah.
And it's proportional to some ni thing here.
Yes.
But it turns out that these n and ni things are gauge. So like in the theory of GR, you can actually fix them to be whatever you want.
Right.
And so you can fix, well, not whatever you want, but like you can fix them.
Yes.
And so you can fix n to be 1 and ni to be 0.
Right.
And that gives you a nice gauge where like you have just this and a spatial slice metric, and here you can actually do the
The separation.
The separation.
Yeah, exactly. Now you can do the thing you talked about. Yeah.
Yes, so you could do it within the ADM formalism, yeah.
Right. That makes sense.
Yeah.
In these global hyperbolic cases, those spectral invariants, are they also spectral invariants then?
Well, so I told you, you get the exact same theory, because if you separate here,
Oh yeah.
like
okay.
like your Laplacian is just going to be the wave operator,
Yeah.
right?
Yeah.
Plus the regular Laplace.
Yeah.
So now you just separate variables, and like if this is on f of xt, you just ask f of x to be t of t and like u of x, and then when you separate variables,
Yes.
you get dt squared t, like t prime prime,
Yeah.
equals minus lambda t
Yeah.
and Laplace f equals lambda f.
Yes.
Something like that, and then now you're just solving the eigenvalue equation. That's how you end up there.
I see.
Yeah.
I see. Okay.
Can I ask back about nothing related?
About the what?
Not related with geometry part.
Yeah.
Sorry.
Yeah.
So you have this triple, you build this manifold.
Yes.
When you choose A to be the functions.
Mhm.
I'm guessing because the only thing I can think is that you want this A to be like you want the if you choose the function, you want this kind of A to be to define your sheaf on your manifold in some way. Like your structure.
Yeah,
sheaf.
I think it sort of like retrieves the smooth structure.
Yeah.
Yeah.
Okay. So. Okay.
Yeah.
Okay, just wanted to make to know. Okay, so I guess yeah. If I change A to be polynomials, then I'll define my structure. Like I'll define my functions to only be polynomials.
Yes.
Okay.
Yeah.
I see.
Yeah, because I think the A gets that smooth structure because there's always that thing where you have to the smooth structures are always crazy. So yeah, I'm pretty sure that's the main thing that you get from A, if I'm not mistaken.
Okay.
Is there anything else? I don't know, but yeah. For polynomials, yeah. I mean, I think I want to say that you can probably also if you're interested in varieties or something like that, you can probably pick functions like polynomials or something like that and get something like that. I want to say, but I'm not so sure. But feels right. Yeah. Yeah. Other questions?
Are these
Yeah.
the only spectral variants you get, or do you sometimes have more? Can you have more?
You do get more. Yes. Oh, you get infinitely many actually.
Or it's gonna be the coefficients of.
Yeah. So basically, this thing is basically the integral of this. Kxxt and Kxx is the sort of fundamental solution. It's like this thing that satisfies delta Kxy equals delta Kxyt equals 0. Sorry, not equals 0. Equals is the heat kernel Kxyt and limit t goes to 0 of k is the delta function. If you think about them as being distributions, and yeah, and so basically this thing, the idea is that on Rn, this thing is very easy. Everyone computes this in quantum mechanics all the time. It's just a Gaussian. Something like this in Rn. But on a Riemannian manifold, this kernel can only be defined. You can write it as e to the minus the Riemannian distance between 2 points on the manifold, but because because we're on a Riemannian manifold, we get the same thing here, like 2 pi t to the n over 2. And then because now it's not necessarily flat, so like we have like we end up getting like a0 xy plus a bunch of correction terms, a1 xyt and so forth. And basically someone showed that this works for, if you pick an epsilon greater than 0 and like things which are like epsilon over 2 away from each other. So you can always do this with and there's a property that like these like a0 of xx is 1 and a1 of xx is the the Ricci scalar, or the scalar curvature divided by 6, and so forth. And there are more, there's infinitely many of these functions, and they're all actually curvature related, because that's the sort of obstruction to like having this being like kind of like this. And with that being the case, when you integrate kxx and you plug this in, of course this goes to 0, but you still have this, and this is 1, so that integrates to the volume. This is the integral of the scalar curvature. The way you get the dimensions is that like they have to have the same kind of singularity, so that this thing for both of them has to have this n be the same.
Okay.
So you get that, and then of course all the other terms which are like curvature related are also spectral invariants.
Holy shit. That's crazy.
Yeah.
What is K called?
K is the heat kernel.
Okay. This is giving me vibes of Green's function propagator type shit.
Yeah, it's also the propagator, or the Green's function.
Okay.
Yeah.
That's crazy.
Yeah.
This is the proof for that Miller gave. Like he just computed this heat kernel and they were the same function. Or,
Yeah. So the proof. Yeah. Okay. Now you're giving me an excuse to talk about that. So the proof of that is basically like, So exactly. You compute the heat kernel for both. Also, the heat kernel for both is the same because they're isospectral.
Yeah. Okay.
So it's like this thing, and this is what's called a theta function for the lattice, and you it's defined for t real of t greater than 0. But you can sort of rotate the entire thing so that it's defined on the upper half plane by just taking it instead of t. And then you can show the property that these things, after you do that, are modular forms. And of a certain weight. In this case, they're weight 8. And there's just a theorem that says that modular forms of weight 8 on a 16-dimensional space is a 1-dimensional space. And so that tells you that what does that tell you? The two heat kernels. That tells you that the two heat kernels have to be constant multiples of each other, but they also have to have the limit going to infinity be the same, so that fixes the constant to be 1.
Yeah.
And so that shows that they're isospectral.
Yeah.
And they're not isometric because of what we said.
Okay.
Yeah. Yeah.
That's crazy.
Yeah.
I guess for completion, what's the definition of an elliptical operator? For that.
Elliptic operator, yeah, you have to define the symbols. There's like these symbols that you can define, which are so essentially like if you write, like let's say you write the Laplacian in local coordinates, like I wrote it before, and it has like this sort of form.
Mm-hmm.
These are like the inverse metric
Yep.
thingies,
Yep.
and lower order derivatives. Essentially, the symbol of delta, and usually the symbol of delta and xi, is like instead of putting vectors here, you put just you know xi, xj.
Mm-hmm. Right.
Okay.
Mm-hmm.
We think about them as being components of a form, let's say. And an elliptic operator is one where this is positive definite, which is clear here.
Yeah.
That's it.
Okay. And the Dirac operator is a specific case of that?
Sure, the Dirac operator is also an elliptic differential operator, yeah.
Okay. Can you write down the Dirac operator?
No.
No.
What, on a general manifold?
Sure.
Like in terms of what?
I don't know. What's the definition of the Dirac operator?
Yeah, that's a whole story. I don't think I can do that. right
Okay.
now, yeah.
Well, because that seems so simple, but it's not simple to write down the Dirac operator?
No, there's a lot of bundles I have to define, and I really, it's going to take
Okay.
too much time. Yeah.
Okay.
Yeah.
Okay.
You need to like talk about the spin frame bundle, and you need to take a representation of the spin group and
Uh-huh.
construct another bundle. Anyway,
Okay.
it's a lot of work.
Okay.
Yeah.
Okay.
But essentially, once you have a Levi-Civita connection on a Riemannian manifold,
Uh-huh.
you build all these bundles, and where like you have spins and representations and blah blah blah, and you can always bring that connection along with you. And the Dirac operator is just the induced connection on the last bundle that you build after you keep going.
Okay. Nice.
Yeah. Okay. Anything else?
Yeah. Awesome.
Thanks, guys. Any questions from online? If anyone's still there? All right.
That's awesome.
Still here.
Cool. Thank you, guys. I'm going to stop the recording.